All right, guys. So in this dice game, you get 0 points for. It's an example that isn't typed in your packet. So just anywhere you can fit it in, like the back of the last page or your own paper is fine. So you get 0 points for rolling an even number. Even number, 5 points for a 3 or 5. And 50 points. Oh yeah. For rolling a 1. Ones are important. All right, so first part here, I want you to find mu and sigma. Well, yes, it's a fair dice, but points are not evenly distributed. But it is a fair die, yes. Yep. You're definitely going to want your calculator for this. Go way back to the first thing we did. Oh.
Like the sum.
Like an expected value.
Mm-hmm. You'll need to use 1 bar stat for this. Talk to each other, think about it. How are we going to find mu and sigma? What numbers do we actually care about? That is a good question. Shane, why are you still growling?
What are you growling?
No.
Growling.
Why?
Okay, what are you making noises about?
Sound. And then repeat it.
Okay. It's going to be a lovely notes recording. Just random noises in the background. Like, yeah, does the probability even really matter in this one?
Sure.
Because they're equal.
Right.
Yeah.
You just do any equal number.
All right, guys, let me write what mu and sigma are, and then we'll see if you got it, and I will obviously go through it. Yeah? All right, so your mu is 10, your sigma is 18.03. Yes? No?
Yes.
Happy? Sad? Sure. So,
Whoa.
that's polars. Yeah, okay.
Second bars. Second bars.
So guys, I could put in like what you're rolling on the die, but do those numbers like really matter when I'm calculating the mu and sigma. No, what matters is the points that I get from those. So this one's 50, 0, 5, 0, 5, 0. Okay, now you could also put in probability in there. What is the probability for rolling a 1, a 2, a 3, a 4, a 5, or a 6? 1 out of 6. It's the same for all of them, right? So does it really matter when you're calculating all of this? It doesn't, because they're all the same. If any of them are different, then absolutely you need that, and you need your frequency list with those probabilities in there. Okay? If you use them and put 1 out of 6, that's great. Some of you I know put like 1 for all of them. That's fine, because it's the same value. What you have to do from here then is calculate. Sorry.
No,
You just really don't need the list 1 that I put in. You could shift everything over. You'd need a list of probabilities somewhere if they were different.
Okay.
Okay? And so then whatever list you put it in. So like here, I care about my list 2, not my list 1.
Oh.
Okay? If I had probabilities that were different, I'd have to put that then, whatever list I had it in, I'd put for frequency. But I didn't put in. Yeah, I'm just doing that. Okay. We got 10 and we got our sigma. Okay.
Is it always going to be this term?
No, it's whatever list you put it in. In list 1, I put the values of the sides of the die, but those have nothing to do with like the mu and sigma of the score. Yeah. Here, you can come grab, Luke, will you come grab mine? It's sitting right up here. You can use that. Just make sure I get it back. Okay. I'll help you remember. All right, we okay with that first part? Okay. We're going to do a little more with the transforming data like we were doing at the end of class last time. So let's say all the point values are double. And guys, on the last part here, find mu and sigma, I really should have said of the point values. I mean, we figured it out, but I should be specific. Okay. Okay, so now all the point values are doubled. Find the new mu and sigma. Are we struggling? In a lot of ways. Okay, do you have to type a whole new list into your calculator? No. Oh, okay. Good. What's the new mu? 20. What's the new sigma? I think is it 06? Right? 36.06?
Yeah.
Wasn't it 18.03?
Yeah.
Okay. Maybe I'm not remembering right. Okay, so good. You remember when you are essentially stretching this, multiplying it by something, you just go ahead and multiply both the mu and the sigma by whatever that number is. Okay, this time let's add 3 to all the original point values. So going back to the original ones. And now again, I want you to find the new mu and sigma. All right, guys, what's your new mu? 13. What's your new sigma? The same, yes, 18.03. Okay, think of it. You shift them all up 3. Does how spread out they are change at all? No. Okay, so your sigma will not change by just adding or subtracting. Okay. Questions on that part, transforming data there? Okay, let's go back into the examples in your packet. I think your next page should be this like small boat thing.
Yep.
Okay. A boat carrying cars across a river. Doesn't sound dangerous at all. Bless you.
Sorry.
Allergies? Yeah, it's getting to that time of year.
I had medicine this morning, but I think it's right.
But yeah, that only lasts so long. And allergy medicine's weird. You have to like take it several days in a row for it to like build up in your system, kind of. Yeah, so good luck. All right, guys, so we've got a small boat carrying cars across a river, and the probability distribution for the number of cars is shown below. So 0 cars, 0.02, 1 car, 0.05, all the way up to 5 cars is 0.42. I want you to find mu and sigma for the number of cars on the boat. Now, probabilities matter this time. Yes.
Is this saying that like the probability of there being 0 cars is like 2% or 0.4?
Yep. Yep.
Okay.
So you guys are going to use your calculator for this again, the 1 bar stat. Give me a minute to key all of this in. Can you see okay?
Yeah, I can see that.
Do you have your packet or not? Oh, okay. I didn't know if you were trying to read the numbers from up here. It could be easier. I just want to make sure you can see what you need to see. Okay. Yes.
Wow, do those to stay filled out?
No, I don't care. Just don't delete the list, just clear it. Okay. Two. Check with your neighbor, see if you got the same mu and sigma. You did not match, okay. What do you think? Like, what'd you try?
I tried L1 and then L2.
So the frequency list should be the probability. Okay. All right, what'd you guys get for mu and sigma? We'll see if you did it right. Anybody want to say their answer? Yeah, I had 3.87 written down, yes. I have 286 written down. I don't know if I wrote the wrong thing or yes. Okay. All right, guys, you should be getting 3.87 and 1.286. Let's stop for a minute and make sure everyone has that.
So it's that and then count it.
Yep.
And then are we doing listed?
So the number of cars will be your like X
Yeah,
list.
but I'm saying like for the 1 bar stat.
So 1 bar stat. Which list did you put your cars in?
I put the cars in the X.
Okay, and then the frequency list.
L1.
Okay, and then your probabilities.
I had that in list 2.
Okay, so for frequency you should do L2.
Okay, so list is L1, frequency is L2.
Frequency will always be your probability. All right, guys. I understand March Madness, trust me, but please, can we like pay attention to and not just be watching the game. Thanks, Lily. All right, cost of a ferry is $5. Calculate the average and standard deviation of the amount of money brought in by the boat. What do you think we're going to do with that $5? Yeah, we're going to multiply it. It's saying you average 3.87 cars per, I don't know, what were we talking about, trip? So if you get $5 per car, you're just going to multiply that by the mu and sigma that you already have. So mu of the money and the sigma of the money of our cars, that's 5 times the 3.87 and 5 times 1.286. Yes, bye. Yep. So what's your average money brought in?
$19.
And 35 cents. Excellent. And what about the standard deviation here?
$6.43.
Good. Okay. Questions on that part? Does it make sense why we're multiplying there? How much, you're telling me how many cars come across, and this is money per car. Okay. Suppose we throw some people on that boat as well. So now we have the distribution for the number of people that ride across on the boat. Okay. And I want you to calculate the cost if you get $1 per person who comes across. It's $1 instead of $5. And we're talking about how much money are we getting just from the people here. Okay, so I want now mu of money for people and sigma of money for people. So you got to do kind of 2 steps in one there. Well, not really, because it's $1, so it doesn't really matter. There's really no multiplying to do. Josh, are you paying attention?
If we have like sub, is that like?
It's not really sub. I could have written
People are like few
dollars of people. So this time, the last one I did like mu of money and sigma of money. I should have put like for cars. That's what we were talking about here, like money for cars.
So it is like a sub.
And now it's like money of people. It's just I didn't write people next to it, but it doesn't have to be a subscript. Just so we know which mu we're talking about. Which money people we're talking about. Yeah, this is a very cheap ferry. I agree. Maybe this is like a really narrow river. I don't know. Oh, well, yeah, maybe this was before gas prices. No, not. This is not a Northern Virginia river. Yeah. Maybe it's an electric boat. Maybe someone's just paddling. Put it on a raft, sure. All right, guys. So, what do you think? What's the mu of money with people this time? How much money are you getting per trip with the people? Excellent. $4.73. What a moneymaker. Okay.
So how do you do that? Like, is it?
Well, I don't know. Maybe we should watch less basketball and we'll know how to do this.
You just punch in all this stuff and then.
Yes,
It's the
English.
same stuff.
It is. I got 2.28.
I know.
Yes.
I did too.
$2.28. Yeah. Okay. All right. This is not on your paper, guys, but let's figure out what's the total money they are making. Yeah, for cars and people. How much do they make for trips? And then the sigma.
So
The sigma you got to think about for a minute here.
is that the adding distributions?
That is the adding distribution stuff. Good job.
Well, I just read it from my notes.
But you saw it. That's good.
Bless you.
Thank you.
Money total. Yes. Tiny money total. Dollars. Yeah, unless these trips take like a minute across the river. Yeah. Well, but what if that was the only way to get your car across? Because there's not a bridge for 200 miles.
I think my car can make it if this is only a missing one.
But it could be a really deep river. It's just narrow.
I'm hoping my car can make it.
Car,
She
you
just
know,
finds a ramp and just like.
just going
My car.
projectile motion now.
Yeah.
If I get this trajectory, I can do it.
It's like a little mystery.
I get your car over there. Or I wouldn't use my car.
So Mr. Lee, what's like the difference in calculating like kilo versus like what's different that you're putting here?
For which one?
Like the top versus the bottom. I got the top of it.
You got the car part.
People.
You got the people part.
Mhm.
So the total, we're now combining cars and people. So,
So it would be
This is
the
the-
plus the mu
and then the sigma you got to think about a little more.
yeah.
So guys, the mu of the total money with people and cars, that's simple and straightforward. You just add the two mu's. So that's your $19.35 plus $4.73, and you get $24.08, I believe.
Sorry.
Yep.
Okay. But I don't just add sigmas. What do I do with sigmas?
You take the square root of each sigma squared added together.
Yes.
It's on the, so we're doing the practice on this page. On this page is the notes for it. It's the adding distribution section.
She's like, I didn't get that far in the video. Yeah, guys, remember, this is where you've got to do square roots. Sigma money car squared plus sigma money people squared. See what we get. This is what you're doing when you're adding or subtracting distributions. You can't just add sigmas. We do all of this. Some good enthusiastic nodding, Lily. I like it. Ooh, okay. What'd you get? Good. Some others are a little distracted today. I didn't say you.
Yeah, but you need to tell me that wasn't a move.
There's quite a few people that could be about today. Lily's like, I see.
All I'm saying is that I can call her a session all the way, and right now it's not easy. I got it right.
Yay!
I don't think all the basketball. Well, I have been playing for months in the finals. That one's looking pretty.
Yeah.
Did you like pick by mascots or something?
I picked mine, which ones I like.
Fair enough.
That's what I did.
You could like pick by colors. Like you could have about as good a shot as.
They are both green. Most of which is very nice. So I'm a fan of that game. But it's not looking so long. It's looking like I might be out.
Risky
In the
move
first
there.
round.
All right, guys. All right. Any questions on this new total money, total people, cars, money business? We okay?
Yes.
All right. Turn the page.
Are we gonna do practice with like the
Binomial and geometric.
stuff?
Is that binomial and geometric stuff?
Yes.
Yes. That's what we're gonna. A good chunk of the quizzes will be on that stuff. Making sure we've got that. Okay. Apparently we're now on example 1. I don't know, but how the numbering went today. So we have Madison swim team. This is their times in the 400-meter relay. I don't believe so. So you've got their individual mean and standard deviation. We want to know the expected time.
Like 3 seconds is a very big standard deviation for a swimmer.
Yeah, it is. You are not consistent. All right, expected time. And what I'm talking about is for the relay, okay?
For all 4 of them?
Yep. How would you find that?
I like the average, the average. The average.
How does a relay time work, guys? Maybe we should go
Oh,
over that
my-
first.
You add them?
Yeah. Yeah, it's just the total time, right, of the 4 legs of the relay?
I read 400, or not the relay part.
I'm
So.
telling you, it's your basketball viewing today that's throwing you off, Josh.
So that's the
There's no way through. Hey.
So you are adding these 4 swimmers together.
Is that it? Or am I overthinking it?
That's it. 224.2 seconds. That's what we would expect their relay time to be. Does that make sense? It's everybody's average time. Combining their average times give you the expected relay time. Okay. Combined standard deviation. How do we do that? I guess I could have just called this view of the team. That might have been easier. Do I just add the standard deviations together? Nope. The square root is there as a hint. Yeah, we did it with just 2 distributions before, but you could combine 10 distributions, and it's the same idea. It's not a quadruple.
Square.
Could you make this, if you wanted to, could you make no. You, no.
So,
Okay.
are you like squaring each thing?
It's just like what we did for cars and people on our little boat across the
I just
river.
didn't know if you could do more.
Oh.
But you just have 4 of them now instead of 2
So
of
you're
them.
still adding distributions?
Yes.
Got it. I keep trying to incorporate the binomial.
I know, you really want to get back to
I
that.
don't even know why. I feel like
I mean,
I
it's
think because when
fun.
we were doing the notes, that felt like it was gonna be like the main part of the unit, you know. So I keep waiting for it to be tied in, and we just aren't.
We haven't gone back to it yet, at all.
You should,
Yep. All right, so you take each individual standard deviation, I think it was 2.8 squared plus 3.0 squared plus 2.6 squared plus 2.7 squared. You should get 5.56 seconds. Okay, clearly emphasizing the standard deviations. You cannot just add them together. Okay, you have to go through this process. Okay, next question's interesting. It's different than anything we've done so far in this unit. What's the likelihood that they will break the school record of 220 seconds? Okay, we are talking probability. They told us this was normally distributed at the beginning. So,
It's 15.
Is it like based on standard deviation? Check standard deviation.
you've got a normal curve. This is of the swimmer's time. So what's the mean? What's the center of this?
200.
Yes, 224.2. That is where it is centered. So where's 220 seconds?
Less.
Somewhere on the left side? Right, yeah, not asking a complicated question here. 220 is somewhere over here, right? We want to know how likely is it that they swim faster than that?
Wait, but why does it say school record of 340?
3 minutes and 40 seconds, which is 220 seconds. We did everything in seconds, not minutes, yeah. Okay, how do we calculate area under a normal curve? Yes, norm CDF. Yes. The shaded part, we're going left to right. So we're going from negative infinity up to that 220. And then we've got our mu of 224.2. And what was the sigma?
5.56.
Yes, you need that combined sigma, okay? What do we get? Do you remember where norm CDF is? Okay, good.
225?
Yes.
Say we don't remember.
Distribution menu, so second cars. Yeah.
Why for this one? Sorry, Ryan. Why for this one do we go to negative infinity, but for the examples we did yesterday, it was from like 0 to a number. Do you know what I'm talking about?
I think so. Let me go back and see which one you were.
It actually wouldn't matter. Because there's no chance that you're going to have a 0 second.
Yeah, I mean, you're not going to go.
Negative, obviously.
Yeah, you can't have negative time, so it's not really going to matter. But just for the sake of like where we're going, it's you go way as far left as you can go. So you certainly could put 0 in there and it'd be fine. Yep. All right, guys. So there's about a 22.5% chance that they're going to break the school record based on this being their times. Yeah, that's pretty good chance. Okay, then part D, what's going to happen to the team's mean and standard deviation if all of the team swimmers' times were cut by 10 seconds? What's going to happen to the mean?
You would drop by 12 seconds.
Well, nope. Yeah, your mu would decrease by 40 seconds. You're making a good comeback here, Josh. Makes sense, right? 10 seconds from each swimmer, total of 40 seconds decrease. What about your sigma? Okay, so we've got our 4 swimmer times here. They all went down by 10 seconds. Good. When we're adding or subtracting, that doesn't change the spread, okay? So sigma would stay the same. Okay, so now what if each swimmer decreased 20% of their time? They got way faster. Is that what? That's a fifth, yes.
So then
You would decrease by a
you
fifth.
would divide that.
Yeah, we don't have to get like crazy here. You could just say they would decrease by 20%. That's fine. Would it be mu and sigma or just one? What would it be?
It's multiplication of both.
It is both. It's like a multiplying thing. That's a stretch, so that's both. So mu and sigma would decrease by 20%. All right, questions on our swimmers here?
Why would the sigma also decrease? Because isn't it just subtracting 20%?
But it's like, it's not the same amount of time from each swimmer.
Right?
20% of someone who swims a minute and 20% of someone who swims 50 seconds is going to be a different amount you're taking off. So it changes how spread apart they are.
Okay. Because it's different amounts.
Mm-hmm. It's the same thing. Think of your grades, like minimum score, let's say, was a 50 on the test and a maximum was 100. If I increase, or maximum's an 80, so I increase everybody's score by 20 points. Adding the same amount to everyone doesn't change how spread out they are.
Right.
But let's say I double all the scores. 50 turns into 100, that turns into 160, like it's a wider spread. So this, if you're decreasing it, it's going to become a narrower spread. Okay. All right, guys, one more example. Go ahead and turn the page. All right, we've got a deck of cards. A deck of cards has 52 cards in it. 4 of them are aces. And here's the gamble we're going to do. You get to draw 1 card from the deck. You win $10 if the card is an ace. Otherwise, you lose $1. If you do this over and over and over, what will the average amount you win or lose on each play equal? Like, what's the expected value here? So long term. So you're playing this game over and over and over. You're drawing a card, put them all back together, draw a card, put them all back together.
Is this geometric?
No. I know. You so want it to be.
It really seems like it would. It doesn't say how many times you're doing
I
that.
know. You're looking for like, so first success, is that anywhere in here? Not yet. So guys, how would we figure this out? What? No, you do? Okay, how many aces are there? 4 out of what? Okay. If I draw one of those, I would win $10, right?
Yes.
Okay. The other outcome that could happen is I could not draw one of those, which would be 48 out of 52. You're not drawing 2 cards here. It's just these are the 2 situations that could happen. You could draw an ace, and this is your probability of an ace, or you could draw not an ace. And with that, you're going to lose $1. So minus $1. So what is this value? What do we get? What are we whatting? What do we get?
I got negative 0.154.
Okay, so we're gonna say negative 15 cents.
Yep.
Negative. That's a really weird way to write that, but yeah. So if you play this a bunch, you can expect to lose 15 cents every time you play. Great game, huh? Now, does that mean when you walk up and play this, you're going to lose 15 cents on that one play? No. Okay. You could not. On one play, you're either winning $10 or losing $1. Oh my goodness. And they're taking 85 cents from you? Or they're taking 15 cents from you and you're, oh dear. Oh, okay. All right, let's try again. So another way we could play this, a deck has 13 hearts. Again, we're drawing one card at a time. If the card you draw is a heart, you win $2. Otherwise, you lose $1. So let's figure out how much money you would win or lose each time on this one. So what am I going to set up for my fractions this time? Times. Okay. Or we could get 39 over 52 times. Okay. What do we get? Are we winning? Are we losing? What are we winning or losing this time? Catch 25.
Yeah.
Yeah? Okay. Try keying it in again.
Is it? What's a 35?
Oh, okay. That explains it. All right. So I get that you're losing a quarter every time. All right, guys. So which game would you play? Neither? Yeah. You'll save your pennies.
I'm not reading anything.
And really, you could argue either one, or you could explain why you don't want to play either, Luke. No? Okay.
I'll play the first one.
Play the first one. Chance for higher wins there. You could win your $10. Yeah. You could argue it either way. You could say I'd play the second one because there's actually a higher probability of winning on your one draw than there is in the first one, but you wouldn't win as much money. So you could argue either way. It's one of these that you just would have to support your argument with a reason.
The first one's was low risk with the chance of a higher reward.
Okay. There you go. It's, yeah, you're more likely to lose, but
it's
you're
a
still
lower
only
amount.
losing $1. Second one, you have a better chance of winning, but you're only winning $2 instead of 10 or something. All right, guys, that's the end of your notes. Let's do some quizzes. We will finally get back to the binomial and geometric distribution here. So, guys, definitely keep your notes out while we go through the quiz.